Good morning and welcome to the CABE webinar Wednesday. Today we're looking at why ventilation must be independently commissioned by a third party with Barry Cope. With buildings becoming more and more airtight, the ventilation installation industry has been exposed as a not fit for purpose. Many new build homes are woefully unventilated, even if the ventilation technically complies with regulations. Much of the issues related to the quality of installation. The persons installing the ventilation are signing off the ventilation as being appropriate, safe, and providing adequate airflow, when indeed none of these are true. The current fail rate is in the high 80% for natural ventilation. This webinar speaks to both inform and promote the use of independent third-party inspections for ventilation systems. My name is Shanika, and I'm the Training and Learning Administrator here at CABE, and I'll be acting as moderator for this morning's session. We strive to create interactive webinars, so we do encourage you to submit any questions you may have during the session. These questions will be addressed at the end of the presentation. We'll go through as many as possible, but if we do run out of time, we will collect any questions and send the answers out in due course. You can also contact webinars@cbuilde.com. If you're watching us live, you can use the side panel to send in your questions. Alternatively, you can get in touch with us via the social links now on screen. Let me introduce today's webinar speaker, Barry Cope, the Group Managing Director of the Building Compliance Testers Association, which operates certification schemes worldwide for parts of the construction industry that are required to demonstrate that they are competent to do the work they do. The largest and most well-known is the Airtightness Testing and Measurement Association, which operates in the UK, Europe, Middle East, Australia, and New Zealand. Barry studied engineering and physics at Oxford, instruments analytical, before moving into the construction industry with BM Trader, now Element, in 2007. Barry spent several years conducting testing and consultancy on buildings for airtightness testing before training in acoustics, designing and building two of only a handful of acoustic sound installation suites in the UK. Barry moved on to be a technical manager at Sight Sound Limited in 2014 before joining BCTA as the general manager in 2015. Barry is passionate about the construction industry, conducting and overseeing training of many trades and parts of the construction industry, becoming an industry advocate for compliance integrity, doing the right thing even when nobody's watching. So if you give me a couple of minutes, I'll pass over to Barry. So Barry, you can start sharing your screen when you are ready.
Fantastic. Welcome, everybody. I'll share my screen there and ask that everybody can see the slides, because I can no longer see you guys particularly well. So can you see my screen, Shanika?
I can, yes.
Fantastic. Okay. Thanks for the very warm welcome. I couldn't have said it better myself. We really try, and everything we do here is about building better buildings. And I'll give a not quite as good as introduction as that, but I will talk and introduce myself as well. So the contents of today's presentation, the title is it's quite salesy. This is quite a technical presentation with a very salesy title. So why ventilation must be independently commissioned. We're gonna go through some of the ventilation in the news, what got Atma into ventilation. We're going to look at some of the basic principles of ventilation, and we're going to look at some of the types of ventilation, focused mainly around what we have here in the UK. I appreciate there's a good few international people on, which is fantastic. We'll look at some of the equipment. We're going to look very, very, very briefly at the commissioning process. We're going to show you some of the installation issues, and we'll have a quick summary. So in not quite as flashy slides as the Chartered Association of Building Engineers, you've already had my introduction. The group managing director of the BCTA group. So we operate worldwide. We operate mainly in the competent person schemes industry, which in the UK means we go and test the buildings once they're built. So we generally do everything at the very end. We have representation as well in Australia, New Zealand, as well as North America through NABCTA. So we do a huge amount of training, normally once every couple of months over in America, normally in Texas. We also operate here the Building Performance Hub, which is our specialist net zero and high performance building training center. where you can learn and sit all of these all of the courses from solar panels to heat pumps. That's my advertising done. By the end of this webinar, you'll be able to understand that measurement or measuring ventilation is a bit more complicated than people give credit for. It's no longer just take your vane anemometer, put it over the fan and tick the box. There's actually quite a bit more to it, especially with the ventilation systems now becoming more and more complicated. You'll be able to understand that we have a ventilation problem in the UK. And to be honest, I think we have a ventilation problem worldwide. There's not a country I've been to in the last 10 years where I haven't stopped and said, this building isn't adequately ventilated, from hotels in nice destinations in the Middle East, Australia, New Zealand. We've been to many countries that don't have an adequate ventilation or have adequate ventilation in their buildings. And it's a worldwide problem. And third, of course, is the slightly salesy approach that there is a solution, and we've created a solution on the back of what we already do for air tightness testing, which is to create a competent person schemes that can be referenced and used to give assurances that the ventilation is compliant, or to not sign it off. And slight trigger warning, this is Awab Ishak. Awab was a 2-year-old boy who spent most of his life suffering, frankly, and a huge part of that problem was that the ventilation in their apartment was just not effective. I won't go into too many of the details because there's still a lot of legal stuff surrounding this, but fundamentally, the coroner's conclusion was that ventilation in the 1-bedroom flat was installed but not effective. And that's kind of the theme throughout this presentation, is that we have 100% compliance on the installation of ventilation in this country. 100% of homes have ventilation installed. It's never the case that it's not. However, the ventilation that is installed is just not effective. And there are simple things that could have been done in these cases where we could have stopped this. So poor Awab died of, I believe it was respiratory failure, as a direct contribution to the development of mold, which was directly caused by the underventilation of the property. We've had doctors report this. So in this case, they've had Manchester GP is calling for home inspections. It's not a new problem. Second and third generation residents suffering with the same health problems rooted in mouldy and damp housing. And we'll cover off some of whether that's underheating. Fundamentally, a lot of this is, some of it is lifestyle choices. Drying clothes indoors is a typical one, but sometimes people just don't have a choice. People don't want to open their windows and turn the heating on because they can't afford to. And we don't have an adequate ventilation strategy installed to deal with the humidity. And this is a favorite. Anyone that follows me on LinkedIn will have seen I actually posted a link to this yesterday. And it would be remiss of me not to discuss the thought that I get, I would probably say on a weekly basis, that airtight homes are the blame for killing people. And this was a wonderful article, admittedly back from 2016, so a little while ago now, titled "Airtightness Blamed for Health Risks in Homes." But the entire article is about ventilation. Airtightness is mentioned almost maybe 2 or 3 times, and this is quite a long article. The rest of it is all about the ventilation not performing, but airtightness gets a real bad stick for this. And part of the problem that has happened in the UK is that the airtightness of homes has come down. So we track those stats. Atma has the best part of 1.5 million tests over the past 10 years showing the reduction in airtightness of homes, but the ventilation industry hasn't caught up. And maybe not the whole ventilation industry. We are installing these things, we are speccing the right ventilation, we're just not checking that it works. And that's the whole point of this presentation. The Zero Carbon Hub put it at 2 in 55 homes tested fully met the guidance on ventilation provisions. 2 in 55 is shocking. is really very bad. Why is that the case? Well, part of that is that the people installing are also the people signing off. We're signing off our own homework. Another part of that problem is ventilation strategies are being selected to comply rather than being the appropriate ventilation. Ian Mordett here from Four Walls was quoted as saying a developer will select a ventilation strategy to help with carbon compliance rather than ventilation. And we can see that all day, every day in the statistics of the air tightness. We'll see people set targets of 5.01. Less than 5, they should be installing continuous mechanical ventilation. So they set the target at 5.01. Inevitably, and in the blower door game, the lower the score, the lower the leakage. Inevitably, in order to achieve 5.01, you actually need to test lower than that. So you're setting yourselves up for failure in the very early doors. The design target can never be met. You're always going to build a home that's more airtight than the ventilation is designed for. And there's no such thing as a building being too airtight, only underventilated in accordance with its airtightness. And I'm the first person, given what we do and how we do it, I'm the first person to stand up and say, if you are not going to adequately ventilate your home, do not make it airtight. But that's the wrong thing really to be saying. We should be making our homes as airtight as feasibly possible. We just need to be better at installing ventilation and commissioning the ventilation. And lastly, Dr. Simon Clark, Associate Professor in Cellular Microbiology, is quoted, mold inside people's homes is nothing new, but its persistence is commonly associated with poor living conditions. It's usually associated with a damp environment and condensation, but even brand new homes can suffer. And moisture can result from lack of heating, but also because of poor ventilation. So it's a really common thing, and there's a huge stereotype around people not heating their homes to get rid of the mold. But you shouldn't need to heat your home if your ventilation strategy is acceptable. So point one of my webinar, why should a third party be used, was it's very clear. There's very clearly a problem. Making buildings more airtight is not the problem. It's the ventilation industry having very little third party checks. The installers are marking their homework, and some of them are scribbling across the page with crayons. One of the reasons Atma got involved with this is that I was on site and I witnessed an electrician sign a document that said they had measured the ventilation strategy. They had put down the flow rates that were required, and they'd signed the commissioning sheet. They had absolutely no idea what a vane anemometer was when they saw us in the plot using one to measure the ventilation that they had just signed off. They had no idea. Yet, because we have a piece of paper in our hand, we can absolve the blame. Well, we've got a bit of paper. I'm building control. I've got my bit of paper that says the ventilation strategy, the ventilation has been measured and done, and therefore I'm okay with that. But the hard reality and the figures don't match up to the level of official compliance. The 2 in 55 homes fail to meet the minimum requirements. This isn't even a good level of ventilation. This is a minimum level of ventilation that's failed to be met. So we'll dive into a bit more of the technical side of this. AIVC defines ventilation is the process by which clean air, and they say normally outdoor air should not ever be called fresh air, particularly if you live in the inner cities. Outdoor air is not fresh air. Clean air is what we should be aiming for. So ventilation is the process by which clean air is intentionally provided to a space and stale air is removed. So that's two things. Every ventilation strategy must have both a supply and an extract. You probably don't think of the trickle vents as the supply, but a lot of the times they are the supply for air that's being pulled out. And it can be accomplished by either natural or mechanical means. So what is effective ventilation? Well, approved document F in England and Wales has a pretty clear and similar strategy. Effective ventilation means that the ventilation system extracts water vapor and indoor air pollutants from areas where they are produced in significant quantities. We generally refer to these as our wet rooms. So it's typically your kitchens, your utility rooms, bathrooms, things where humidity or cooking gases and oils and things will get put into the atmosphere before they spread through the building, and supplies a minimum level of outdoor air for occupants' health, rapidly dilutes indoor air pollutants and disperses water vapor. Minimizes the entry of external air pollutants. That's interesting. With an MVHR system, you can do that with filters, but generally you minimize the entry of external air pollutants simply by making your building airtight. But also produces low levels of noise, offers easy access for maintenance, and provides protection from cold drafts. These are the three things that are very, very much being ignored. We'll cover off some of those a little bit later. So why do we ventilate? Well, we need to remove those pollutants, the VOCs, the carbon monoxide, allergens, such as pollen. These things we need to maintain healthy indoor air quality. You will be surprised if you've ever put an air quality meter near a cooker or gas hobs and seen what is created when we cook. For those of you that don't turn on your kitchen cooker hood when you cook, you probably will after this presentation. So we need to regulate the temperature. Ventilation can help regulate the temperature inside a house by allowing fresh air to enter and hot air to escape. And that can help maintain the indoor environment. We need to control moisture levels. Moisture levels is huge. We don't generally have a huge moisture problem in the UK, not like we have in New Zealand, not like we have in Australia, not like we have in the Middle East. Ventilation is so important to get rid of the humidity and moisture that's inside our homes. They will damage building materials if you constantly have condensation landing on your building materials and you don't have an effective air tightness, moisture, and ventilation strategy. Other things and this is the area that really interests me, is about cognitive function. So research has shown that proper ventilation can improve cognitive function, particularly in office buildings and schools. And there's an incredible study that I haven't referenced that was done not so long ago that shows they cross-referenced a bunch of schools with CO2 monitors in the examination halls, and they found that the lower the CO2 buildup, the higher the exam results. I think from memory it was around 15% improvement in examination results in a low CO2 buildup building, which is pretty impressive, and one of the reasons we actually installed an MVHR system in our office here. So we also need to reduce the spread of airborne pathogens. You'll all know COVID hit the world really very hard, and suddenly for about a year it made ventilation really sexy again. But that all seems to have disappeared again now. We're back to doing what we normally do. We're back to sitting in shops with condensation all over the windows. We're back to sharing stuff we shouldn't be sharing. And ventilation no longer is really at the top of the agenda. But for a while it was, and we looked at CO2 and we looked at the way we remove pollutants and bacteria and viruses and things from buildings. Ventilation is also important to reduce the spread of odors. We don't always talk about it, guys, but from cooking and from the bathroom, we need to remove those smells. So in summary, ventilating buildings is really important for maintaining a healthy indoor environment, regulating temperature and moisture levels, and reducing the spread of those airborne pathogens. So what's the main causes of poor air quality in homes? We'll go over some of the similar stuff, but fundamentally, it's a lack of ventilation, a lack of it. And that's not a lack of installed ventilation, that's a lack of effective ventilation. Just because you have a fan in your house that spins and makes a bunch of noise doesn't mean it's actually pulling out much air. Insufficient ventilation can lead to the buildup of the pollutants and the organic compounds. So fundamentally, ventilation is a leading cause of poor air quality in our homes. Combustion byproducts, as I discussed earlier, gas stoves, furnaces, water heaters, They all release pollutants such as carbon monoxide, nitrogen dioxide. We need to get rid of this stuff. We need this stuff to be extracted as quickly as possible from our homes. Smoking, hopefully there's not too many smokers, and I know smoking is in decline. Huge amounts of harmful chemicals in cigarettes. And sorry if you're having your breakfast while you watch the presentation. Things like formaldehyde is not very good. And mold and moisture from humidity, inadequate ventilation, it leads to the growth of mold, and mold, it can be fatal. It's really very damaging. Some of you might not quite understand, but household products, a lot of the products you use to clean contain some really harmful, nasty things. Some of the cleaning products, they might leave your surface without any germs, but they, they'll really damage the air quality in your home. So having an effective ventilation system means you can do both. And inevitably, there's always people every year that are hugely affected by pollen. So being able to actually lock down your building, as it were, and maintain that good air quality through filtered ventilation can substantially improve your sleep quality, and it can reduce your symptoms. So it's important to address the causes of poor indoor air quality to maintain a healthy and comfortable living environment. Regular maintenance of ventilation systems is something that we also need to consider. So I know these slides are very wordy, and I'm going over the same points, but it's really important that ventilation is taken much more seriously, because we all think of ventilation as something that we don't necessarily think of as something tangible, but actually behind the scenes it's causing damage. So condensation, by having huge amounts of moisture in the air, will lead to mold growth, peeling paint, damage to those building materials. A lot of this stuff can happen behind the scenes. So I won't go over too many of these slides, but I will pick up on this one. The main causes of condensation in homes, one of these is actually air leaks. So by having air leaks, you can allow warm, moist air to enter areas where they are typically cooler, such as attics and basements and crawl spaces, which can lead to condensation, which ultimately will lead to degradation. I've been involved in cases where we've seen the attics of buildings that are 10 years old have been completely destroyed and have had to be replaced 10 years in, because they had fans venting directly into the attic space, and that moisture was getting trapped, which caused the timbers to rot. So air leaks, really very important, and then insulation is also incredibly important as well, to maintain temperature differences. We normally, during our courses, we'll talk about dew point, and to calculate the dew point to see when you're likely to have problems. I won't cover too much of this, but what I will leave you with this is an average family creates the equivalent of 10 glasses of water in their home each day simply by breathing, boiling a kettle, showering, and cooking. Most will normally be removed by ventilating. So without ventilating, without effective ventilation, where does that moisture go? Doesn't bear thinking about. So I thought I'd stick in a couple of fun slides. But Barry, houses need to breathe. There's not a day that goes by in my life that somebody doesn't shout at me on one of the courses, or shout at me on LinkedIn and say, Barry, houses need to breathe. Yeah, houses need to breathe. We'll look at this one. So do the humans. The humans need to breathe. And I think that you'll find that's a lot more important. So homes becoming more efficient, more airtight, have exposed the ventilation industry for underperforming. And I want to be super clear, I don't mean the ventilation industry because they're doing wonderful things. What I really mean is that we're installing the products badly. The installation of the ventilation has been underperforming. So ventilation is incredibly important, yet because it's not seen and it's not heard, it's not tangible, it's generally moved to the less important pile. Fire will kill you pretty quickly. A structural failure will kill you pretty quickly. Ventilation will kill you slowly. It will take 2 years, but it will kill you slowly. So it is moved to the less important pile, and we need to bump that up the list. So ventilation strategy, in the UK building regulations, we kind of have 4 strategies that are discussed. Natural ventilation, which is where we would have an intermittent fan in the bathroom and normally your kitchen cooker hood. And then you'd have trickle vents scattered around the house, and you rely on the wind. If you're relying on the wind actually doing something, that's a pretty weird way of ventilating your home. Hopefully I can do a quick annotation here. If your house here sits on top of a hill and you have a natural ventilation strategy and the wind cuts across, then you'd have pretty good natural ventilation. But on the flip side, if your house sits in a valley, the wind zips across the top of the valley, you have pretty poor ventilation. Your natural ventilation strategy falls completely flat. You have almost no ventilation whatsoever. The other thing I get that I'll address here is that the air permeability is used to define the ventilation strategy in the regulations, and that's just wrong. It's wrong because this building here may have a ventilation or an air tightness test of 2, which is considered very low, and be okay because the air's zipping through it. This one may have an air leakage of 10, which is really very bad, but not be any good because the air is not passing through the building. So we need to get a lot better at looking at and not using air permeability in place of air infiltration. If any of you guys are interested in discussing that further, you can come on our training course. The second one we have passive stack ventilation. It's all but gone from the regulations now. That involved just making holes in the building and relying on the stack effect to remove ventilation. Mechanical extract ventilation, sometimes called multi-point extract ventilation, is normally where you have a centralized system that pulls air very slowly but continuously from all of your wet rooms, and theoretically then pulling air in from your dry rooms, your living rooms, your studies, your offices, and pulls the air around the building, so you get a continuous flow, but because it runs slowly, normally very quietly. Mechanical extract ventilation with heat recovery is pretty much the best way you can ventilate your property. It's the thing that everybody's raving about right now. We do actually have 2 more strategies that generally are fitting in nicely with retrofit. So these are decentralized continuous extract ventilation. So instead of it being a centralized point, you'll have smaller fans dotted around that continuously run. We also now have MVHR versions of those. They're less common, quite cool technology, rapidly growing technology, but a push-pull system to allow your house to breathe. So they extract air for 60 seconds or so, and they pull air in. And they have a heat cell in the middle that heats up when the air's being taken out of your home. And then when the cold air from outside is being pulled into your home, it goes through the heat cell and warms up. And that system works the other way around if you needed to. And of course, just for the sake of this, we have the slides. We give everything an acronym in this industry. So whenever you see a small D in front of MEV or a small D in front of MVHR, what we mean is that it's actually decentralized. Let me just see if I can get rid of these drawings. Realize they would stay on the screen. There we go. So we used to refer to these as systems. So if I use the word system, generally we used to have system 1, 2, 3, and 4, and we're still trying to transition from that language. So extract ventilation, or system 1, as we used to call it, is normally intermittent extract ventilations, which turn on normally when you touch the light switch in your house. The fan will run for 15 minutes or so. We have background trickle ventilators that act as the supply ventilation. So as the room gets depressurized from the fan, that runs, the air will then come through the trickle vents or be pulled through the trickle vents in order to resupply the air. They look like this. Typically singular fan installed somewhere. You can have them running in line, so you don't have to hear the noise of them. Your kitchen cooker hood is technically part of your System 1 strategy. And you can also now have these very fancy vents that are built into your cooker. So with extract ventilation, you put a fan in all of your wet rooms, your kitchens, utilities, bathrooms, and sanitary. In the new regs in England and Wales, the sanitary accommodation, i.e. the toilet or the powder room, normally the toilet under the stairs, or just as you enter, that can be achieved using purge ventilation. So you don't have to actually put a fan in the small bathrooms now if you have an openable window. In Scotland, they have this area, which is this designated drying area for drying clothes. My wife being Scottish, I'm allowed to make jokes about how they can't hang their washing outside because it's always raining. So they have a designated drying area, which has a separate requirement. So extract fans should be as high as possible in the room because warm air rises. We want to take the air from the top of the ceiling, and where cooker hoods are installed, they have to be installed as per manufacturer's instructions, or we give some loose guidance in approved document F. Extract fans, cookers, I've done that one. So for System 1, we simply have very simple numbers. If you install a cooker hood extract into the outside, it needs to achieve 30 litres a second. If you have a fan in your utility room, 30 litres a second. Your bathroom is 15 litres a second, and any sanitary accommodation that doesn't have a window or a window that can't be opened, you might be on a busy street, for example, so you need to achieve 6 litres a second. And you think these targets are nice and easy, right? You go to your builder's merchants, you buy a fan that says that it achieves 30 litres a second. You install it in your wall, you connect some flexi duct to it. Will that achieve 30 litres a second? Nowhere near. A very small run of flexi duct can reduce the performance of the fan by as much as 70 to 80%. It's not uncommon for us to go and measure properties where the bathroom fan needs to achieve 15 litres a second and it's only achieving 4 litres a second. We'll discuss that in a little bit. It should be very easy. You should buy a product off the shelf, but it's not that easy. So the process of measuring it, reasonably simple. It gets a bit more complicated. In Scotland, they have very similar targets. The only difference is with the toilet or the WC or the powder room, you have to do a calculation rather than give a limit. You do a calculation based on the size of the room. So there's 3 main methods for commissioning ventilation systems depending on the equipment you use. Our preferred is method A, which is the unconditional method. Method B is the conditional method, and C is the minimum benchmark. We'll go through these one by one. In the Atma Domestic Ventilation Commissioning Certification Scheme, which we're yet to come up with a more catchy name for, we don't allow the minimum benchmark method to be used as a method for compliance. I'll discuss why in a minute. So the unconditional method, method A, simply measures the supply or extract ventilation rate accurately, almost instantaneously with a high level of accuracy. In order to do that, you'll use a powered flow hood. I've got a picture on the next slide. So inside the powered flow hood is a small fan, and what effectively happens is that fan will run and match the airflow speed of the airflow that's coming out of the device, and it will effectively balance the pressure, and then it will give you an accurate reading of how much air is coming out of that particular device within around 5% margin of error, which is pretty good. You turn it on, takes maybe 10 seconds for the fan to spin up, and it will give you a reading. There's 2 main ones on the market. There's the observer to diff, which there's also the Akin Instrumentum Flow Finder. Both will cost you around £2,500, and you'll need to get them calibrated every year. But the time savings are pretty substantial if you're doing this all day, every day. The conditional method uses vane anemometers, which are substantially cheaper. You could spend maybe £400 or £500 on a vane anemometer to measure the airflow. So you think, great, I could buy 4 of those, 5 of those for the cost of a powered flow hood, but you'd have to account for the time. The key thing with the vane anemometer, and I catch people out with this all the time, the indicated flow speed is not the measured flow speed. So what you see on your screen is not the amount of air that's coming through the fan. I see it all the time on LinkedIn where people are using vane anemometers to measure flow rates through fans, and it's just not the right number. The reason for that is that the vane anemometer itself creates a back pressure, which isn't accounted for. What effectively happens is the vane anemometer is usually a 100 millimeter device, 4 inches, if anyone's in America. If the hole in your fan is 4 inches and your ductwork is 4 inches, then the vane anemometer is actually pretty close. It's not going to be far off. If your device is the fan or the ducting is any bigger than that, your vane anemometer will not give you the correct flow reading. It will create a back pressure, which will reduce the speed of the fan because of the back pressure, and therefore it will give you a lower ventilation reading. So the conditional method B, can only be used for intermittent fans and decentralized MEV, where the correction factors of both the instrument and the fan are accessible. Because the vane anemometer produces that back pressure, as I say, ideally you should have the flow hood should be 50 millimeters greater than that of the fan being measured. And as I discussed, 100 millimeter, anything less than 100 millimeter vane anemometer can't be used in our scheme. So when I mentioned that the vane anemometer is 5 times cheaper than a powered flow hood, here is what you need to do in order to calculate every single individual fan. You need to make sure that you've got the correct numbers and correct calibration data installed into your device. And that will change. There's normally 4 different calibration factors you need to add into your device, depending on the fan speed, depending on whether you're measuring positive and negative. So generally 4 different correction factors, and you'll need to change those if you go from a utility room to a bathroom every single time. You'll need to find the pressure drop from the anemometer curve. What I'll actually do is run through an example as we discuss this. So let's assume we have an indicated flow rate of 12.6 liters per second on an airflow QT 100T bathroom fan. Let's bring up our performance graph and we'll measure the drop. So there's your calibration certificate, and you can actually see here, and if you've got a big enough screen, you have 4 effective areas, and these effective areas have to be entered every time you change the configuration of your device. Depending, you can also, in our example here, we have a hood 2 can only be used for certain. You have to change that again. So depending on the hood you're using, you may have to keep amending your equipment. So we've measured 12.6 liters a second. We convert that into meters cubed. We find this on the graph. We come over to our pressure drop. So what we've got in our pressure drop there is 6 pascals. So this is the area we're looking. Hopefully you can see my mouse. So we've measured 6 pascals of pressure drop. What we do is take our 12.6 liters a second. We move it across to the static pressure. We move down the static pressure, the 6 pascals that we measured. We move across, we move down, and therefore the actual fan flow rate in this occasion is 15.5 liters a second, which is compliant. So it's very easy for us to look at a fan, measure 12 liters a second, and assume that that's a failure, when actually you need to use the correction factor, which would prove that the fan actually is doing the right job. So suddenly your £500 piece of equipment now adds in an additional process for every fan that needs to be measured. Now, to combat this, the industry, not us, but the industry came up with a method C, a minimum benchmark method. And effectively what they do, you still have to do all the same stuff. But if your fan flow target is 15 liters a second and you put your device over, you'll get 12 liters a second. It's assumed that that's okay. 30 liters a second, if your reading is 24 liters a second, again, same thing. And 60, you can actually see here the substantial back pressure. So generally a 15 liters a second fan will have a 100 mil hole, and you can see the back pressure is very little. If that fan was actually achieving 18, 19 liters a second, your indicated speed will be greater than 15 liters a second anyway, so you're not so concerned. But when you're targeting 60 liters a second, you're generally looking at 150 on 175, maybe even a 200 millimeter fan. You can see the back pressure created by the vane anemometer almost halves the indicated reading. So the method C effectively says, as long as we get 35, then we think it's enough. We think that's okay. We don't allow that because it's not an accurate scientific measurement, and it's just not the way the industry should work. But it's a workaround while the airflow, while the ventilation industry haven't all published their fan correction curves. Very quickly, a couple of really important things when we're measuring intermittent fans is that we need to go through a whole process. Now, I'm not going to go through the entire procedure, but you can see the procedure's not little. One of the key things that we have to do is we need to make sure that we're closing the door and closing the trickle vent when we take the measurement. And that's because, if you remember quite a few slides ago, I said that all ventilation must have an extract and must have a supply. If you don't have, if you have an extract without a supply, it's a bit like if any of you guys have been to McDonald's and had a milkshake and you try and suck the milkshake through the straw. What you're effectively doing is creating a negative pressure in the straw, but you're not getting any supply of the milkshake because you've created you don't have any ability to create that supply. So normally you'd have undercuts in the door and you'd have trickle vents in the bathroom itself, and that is your supply. But we measure with those things closed because that might be how the building is used in practice. You might find that the person living there has closed the trickle vents, it closes the bathroom door because they don't want to shower with the door open. And therefore, even though the fan is running, you might just be pulling a pressure on the building without actually removing very much air at all. So that's one of the things that gets checked. So even though a fan might make a noise, doesn't mean it's moving very much air at all. Continuous extract ventilation. So this is the one I discussed. We have generally a centralized unit. We run those to each of the wet rooms, and we very, very slowly pull out the air that's in those rooms. This means that all the noise happens in this little box, which is not generally inside your home. Just to note, you will get penalized for installing these things outside of the conditioned envelope these days. But these run very slowly, generally 4, 5, 6 liters a second. They're almost perfectly silent. You can't hear them. And they pull out a very, very small amount of air 24 hours a day. You can also have a boost mode on them, which enables you to boost when you're cooking or showering. They're also getting very clever now. You can have CO2 sensors, you can have humidity sensors, and these things will move up and down as and when they need to. But this is also, it doesn't come without a bunch of mathematics required to do this properly. So we have to calculate our continuous rate and our high rate. So the continuous rate, we use a secondary table, and the high rate, we're given minimum high rate numbers in the figures here. So we work out by doing this in England by the number of bedrooms, and that will work out the total extract rate for a property. Now, what's incredible, what I always think about is that in a 3-bedroom average house in the UK, you can think of a general 3-bedroom semi-detached, the regulation requires us to pull 31 liters a second out of the entire house to be compliant. And when you think back to having just trickle vents as your general supply or your general way of ventilating a building, are those trickle vents pulling out 31 liters a second from that house in order to make that ventilation effective? They're definitely not. So the level of ventilation is pretty big. It's pretty huge. So these are very, very effective systems, very, very efficient systems. They do an incredible job of moving air around a home, and they're almost silent. So we work out the continuous rate. We also do it by footprint. So if you have a house with particularly big bedrooms, we'll have a correction for footprint. In Northern Ireland, we have the same. Their continuous rate is a little lower, but they have a correction for occupancy. So if you know there's going to be more occupants, you actually increase the required background ventilation. So once we work out continuous rates, we'll then look at our high rates and make sure that all of these comply. And there's the numbers for Northern Ireland, just in the slides for your east. And the occupancy rate is, they tell you what they expect the occupancy to be. And if you know it's going to be more, as the commissioner, you need to add more flow rates. And in Scotland, they're different again, but that's all accounted for. In Scotland, we actually use a much easier way of assigning flow into the room. And in the Atma certification scheme, if you select any country other than England, Wales, and Northern Ireland, it will use this approach. So it will take half the volume of the property and convert that into liters a second. So half the volume is quite a lot. So if you have a 250 meters cubed house, we'll take the 125 meters cubed and turn that into liters a second, and it'll give you your requirement. Very effective way of doing it, actually, and a very easy way to spec. If that was written into the England and Wales building regulations, life would be a lot easier for a lot more people. We also have the MVHR system then. So MVHR system has, in effect, the same thing. And again, note that you shouldn't really install these in the loft. But instead of just extracting from the wet areas, we also supply into the dry areas via this MVHR system. And what happens here is the warm, stale air from your bathrooms and your kitchens goes through a heat exchanger and is dumped outside. And then outdoor air, which might be dirty air, comes in, is filtered, goes back through the heat exchanger so it warms up, and then is brought into your habitable rooms. And it's generally decentralized. There's an image showing kind of how the inside of these things look. So we need to do a bunch more calculations, and the calculations themselves are actually the same or very, very similar. And I'm not going to go through how we do the calculations, but effectively that whole MEV process is done again in reverse for the supply side. So there's a lot of maths involved in getting these things right. So just installing them and spinning the little discs around until you can't hear much of a noise is not okay. I won't go through the entire process, but you can see the procedures. It's lengthy. There's a lot that needs to be done in order to get one of these systems in one plot working. It's not just a case of putting a vane anemometer over a fan and calling it okay. This takes longer than an air test to get right in each home. So once they complete the balancing, we also record the information for on the sheet for the commissioning. So we're checking, is the machine noisy? Can we get access to the machine? We'll cover some of those things in a moment. So we complete this digitally using the Atma ADV CCS. If anybody can come up with a better acronym or better name for that, then do let me know in the chat box. So the process for commissioning isn't straightforward. This is why a third-party system should be used. So commissioning of ventilation systems requires a lot more than simply holding up a manometer to a fan and saying, yes, it requires background calculations, corrections, balances, checks, and so much more before it can be signed off. So why bother? At this point, you're likely thinking, what's the problem? I've been through all of that stuff. The building regulations sets very clear targets. The building regulations gives very specific installation requirements. So why is there an issue? Why is there an issue in the UK with ventilation? So let's look at some of those very quickly then. So 1.74 of approved document F, ventilation system should be installed to meet the following conditions, should comply with the guidance in the document and not compromise the performance of the system. Adequate space should be available for access to maintain the ventilation equipment. Do we think that's a good way of installing a fan? Cutting a hole in the ceiling, chopping it through? Is that effective ventilation? Are we going to be pulling air from the ceiling void or from the room? Most likely the ceiling void. How on earth do we even measure that as well? Ventilations, they should be installed with adequate space for access. Well, these two images by Nathan Wood, guys, definitely follow Nathan Wood on LinkedIn. He's a real good guy. These two ventilation strategies, this is Mr. Xbox 95, which there's quite a few of these kicking around. Very simple machine. You need to be able to pull the filters out and change the filters at least annually, if not every 3 months, depending on the air quality outside of where you live. You also need to be able to pull out the heat cell once a year and run it under warm water to get rid of any contaminants that may be in there to keep the system operating effectively. Both these two examples, you can't do that. So it's been installed. It might be okay, it might be working, but you can't maintain it. That would not have been okay in the Atma scheme. Here we have another one. Is this okay? We can maybe get the filters out of there, but can we get the heat cell out? No, the heat cell can never come out unless the entire system is taken off the wall and pulled out, and that's not how it's designed to be used. So rigid ducts must be used wherever possible. How much airflow do you think is going through this duct? It's been chucked across the top of one of the rafters there. That has zero airflow. So the rigid ducting should be used. As soon as we crush these ducts like this, every bend creates something like a 4 Pascal pressure drop in the system. This is probably a 50 Pascal pressure drop in a system that's only producing 200 Pascals. We're losing a substantial amount of our airflow here because we've got a really poorly designed and really poorly installed strategy. We've even gone as far as using proper solid rigid ductwork to create the 90-degree bends, and then we've just bodged it at the end. Not good enough. Flexible ducting should only be used for final connections. Length should be a maximum of 1.5 meters and meet the standard of BISRIA's BG 43 2013, which ironically says lengths should be less, flexible ductwork should be less than 1 meter. You have a big contradiction right there in only, 12 words or something in the regulations. So flexible ducts should be installed so that the full internal diameter is maintained and flow resistance is minimized. We need to pull the duct taut. We need to ensure that ductwork does not pass through orifices with a smaller diameter than the duct itself. Do we think this is pulled taut? This is just absolutely shocking. We've got this ductwork not pulled taut. We've got unnecessary bends. We're not maintaining the full diameter of the ducting. I'm not entirely sure if it's going down there or around the corner, but this isn't good enough. That should be rigid ducting all the way, and if anything, a very small piece of flexible ducting. If I was sitting in local government right now, or even HSE, I'd be banning this stuff. I'd be saying you can't use flexible ducting unless it's less than 30 centimeters. This is just not okay. So they should be, duct connections should be mechanically secured and adequately sealed to prevent leaks. Rigid connectors and Jubilee clips should be used, and the installer should make a visual inspection to confirm both of the following. There are no obvious defects and all the packaging has been removed. Well, is that okay? Someone signed off on that. Is that okay? I think it's an American one, but this is a point in case. They just ducted it to the roof and it's chucking all the lint from the tumble dryer. But this is the stuff we're seeing daily in homes. Look at this one. We've got ducting here that runs. This one isn't even connected on the left-hand side. These have come off the junction box. On the right-hand side here, this is one from the UK. Somebody has signed the form and somebody has inspected this property and accepted that this is okay. There's no airflow through this duct on the right-hand side here whatsoever. It's almost zero. Is that okay? No, it's not okay. We've got to do better, guys. We have another flexible duct, but don't worry, we've got some duct tape on it. We've got some silver foil tape. Is this producing any airflow whatsoever? Absolutely zero. And here we've got another unit where, admittedly, we tried our best. We've used a bit of flexible ducting, but it's popped off during the installation. Customers complained that their ventilation system isn't really doing anything, possibly got mold starting to appear in their property. And this is what we find. So why should a third party be used? Well, there's very clearly a competence issue. So what does Atma do that is going to fix what you've seen on these previous slides? Absolutely nothing. Of those slides I just showed you, all the pictures, the Atma ventilation scheme is going to do nothing. And by that, what we mean is, if any of these had been inspected by a member on the Atma ventilation certification scheme, none of these things would have been accepted. None of them. It would have been rejected. It would have gone back to the installer to say, you failed to meet the airflow requirements. You failed to meet the commissioning requirements. You need to go back and take another look at that. And that alone, those pictures, is why third-party commissioning needs to be done. It's been in the building regulations for 13 years that that a commissioner needs to sign off on this stuff. 13 years. But Atma have now got involved. We've created a scheme to make sure that we can do this. I've got a couple of minutes left, so let me very quickly show you this. We might have time for a couple of quick questions. So this is the Atma ventilation lodgement system. In very simple terms, this also works on the Atma app if you are qualified. So we add all of the rooms down the left-hand side. We add the volumes and the sizes. We click to take a picture of the unit that's been installed or the particular fan. We also add a picture of the barcode or serial number or install label of the device as well. That all happens nicely in the app. We add in the serial number, and what we see here is the target flow rates are automatically calculated for us. So if I just very quickly run these through, what I'll actually do is just do, here's one I did earlier. Let's pop out this one. Bear with me a second while I open it. I'll move that over onto this screen. And there we can see, just like with the air tightness world, here is a simple certificate in one page. It's actually 2 pages. The second page is all the questions that are required in approved document F. Here we have all of our flow rates that we've added. It shows the wet rooms, the dry rooms, the target flow rate, the measured flow rate. It shows the whole dwelling extraction. And if any of you guys right now have your phone in your hand, scan the QR code. It will show you an image of this certificate. It will show you everything you need to see to verify that this certificate is true and valid and that it is of a live member and hasn't been recalled for any reason. The whole system is now ready. It just needs to be specified, and people insist that these are getting used. And we're now making very good progress with huge amounts of housing associations, as well as national house builders who are now specifying that you need to be Atma registered. So we're really pushing the scheme as a way of having a third-party assurance. Each of these lodgement certificates, we do all of those calculations for you, give you access to the app, £1.75. Now tell me that's not an absolute bargain for all of the effort that happens right there. So that is the end of my presentations. I'm more than happy to take questions for the time that we have left here, and you can definitely contact me very easily. Just simply barry@atma.org. Most of you have got my email address anyway, and I will happily take any questions you may have. I'm not sure any of you are going to be able to ask me any questions. Shanika, are you there?
Yes, I'm here. We have one question. Can you comment on testing of individual intermittent extra fan, and are these capable of adjustment?
So generally, no, but they don't need to be. So the individual intermittent extract fans just do one job. They are on or off. Therefore, when they are on, they need to operate to the right level. The decentralized fans that you can use in place of those can be adjusted. So you can adjust them to have an everyday trickle mode that just constantly pulls out a very small amount of air. And you can have them adjusted for boost mode. So you can choose the trickle and the boost depending on what your preferences are. We as the commissioners, we will always set them to the minimum level as required by the building regulations.
Thank you. Does anyone else have any more questions? This is the time to submit them. We'll give them a couple of minutes. It may be the case that once it's recorded, I'll get it after and I'll send you them over via email if that's all right. We have one. Yes, I can do that.
I believe, is it going on YouTube?
It is.
Yeah. It's further. You'll see this on.
Links, yeah. Oh, I've got a question here. What qualifications do I need to design a ventilation system for domestic properties?
Good question. This certification scheme and the way that ventilation is going to change in the near future is that it's going to be broken down into 4 distinct sections, and they could be 4 different people or potentially 2 different people. So the first section is design. Somebody needs to design the ventilation strategy. The second is install. So somebody installs it based on the design. The third is commissioning, which is us. And the fourth is maintenance, which is an industry that's rapidly growing. To design ventilation systems, there is no official qualification. There is no, as far as I'm aware, there's no official training course either. But watch this space. We're currently designing an install ventilation course here at the Building Performance Hub. And once that's done, we will design a ventilation training course as well. But as of right now, there isn't any official courses that I'm aware of.
Thank you. Can trickle vents be eliminated?
Yeah, trickle vents absolutely should be eliminated because we should use mechanical ventilation for both supply and extract. That is the very best way. Trickle vents do 2 jobs. One of those is okay, which is allows air to be supplied into a room. The second of those is this cross ventilation, which is very hit or miss as per the little drawing I made for you earlier, depending on the exposure level of your home, depending on lots of other factors. They do or don't work. The best ventilation strategy is to eliminate trickle vents, which is what you would do with MVHR. You don't have any trickle vents with MVHR.
Okay. Why are kitchen installers telling house owners, not cooker hoods, do not need to extract open air?
That's the exact problem that this my presentation highlights, is that the installers aren't getting it right, and that needs to be stopped. If somebody's telling you that cooker hoods don't need to extract to open air, then they're wrong. They do need to. If they don't, you need to have a separate fan that does. That's image 2 in approved document F, assuming you're in England and Wales.
Okay. Which system would you recommend as being the most appropriate for retrofit?
So for retrofit, you'd have to look at each home independently. I always start from the top down. The best you can possibly have is a centralized MVHR system. That's generally accepted as the best. If you can't have that, then you should take a step down and see if you can install decentralized MVHR, which is quite pricey. If your budget doesn't allow for that, you then go down to the next best thing, which is centralized MEV, and you'll go down and down and down. So I always say for retrofit, you install the best that you possibly can, and you work your way down the list for whatever varying factors you have. So MVHR isn't always easy to retrofit because the joists and the room layouts might not allow for an easy install. So you work your way down. As a minimum, I would install decentralized MEV fans, the ones that run continuously. That's the bare minimum that should be installed in every retrofit in this country. When I become Prime Minister, that's the law.
Okay. Our competency schemes, high barrier competency schemes are only any use if the scheme provider randomly checks on site installations that have been assessed. Will Atma carry this out?
Absolutely. For those of you that know, one of the very successful things that our SIPMA scheme does is requires testers to lodge their locations in advance. And we employ people specifically who turn up unannounced on building sites to check the work that's being done. The beauty of ventilation is that we can just go back and check it. It doesn't stop people with balancing of MVHR systems, such as, air testers will spin the little devices and ruin somebody's balancing. But fundamentally, the fact that they have to take a picture proves they were there. The fact that they will have to measure a total flow rate because all those flow rates get added up is there. And those are the things that we can check. If somebody claims, if one of our members were to claim a ventilation system, for example, was able to produce 50 litres a second across all of the vents, and we go back and measure it and it only achieves 30 with all of the vents wide open, we know that that tester won't have met the minimum requirements of the scheme and will be removed. And my job this afternoon is to remove an airtightness tester who's just about to be kicked out of the scheme. We do it on far too commonly, unfortunately. Yes, we will be going and checking those.
Thank you. Slightly separate topic, but are you aware of any accredited course for TM59 calculations on its way, or simply Part O calculations?
Yeah, the Part O calculations we are looking at ourselves. I don't know where there are any accredited courses. SIBSE probably is a pretty good place to start. That's the people I would be asking. Potentially CAVE as well themselves might have some knowledge, but I don't know any. I wouldn't recommend any because I haven't been on any that do currently exist.
Thank you. So we'll do the last question. I'll send any more via email. Do you believe the introduction of approved document O, overheating and ventilation, is a move in the right direction for ventilation?
Yes and no. It is because we need to deal with overheating, which is a big problem, and that's document O is all about overheating. The way they've gone about it and some of the calculations, I've seen a paper, and Jack Harvey Clark's quite a good advocate of this, is that there is a paper that shows some of the human thresholds might be a little bit out. So, and therefore we might be shooting ourselves in the foot a little bit with some of the numbers in there. But approved document O is good. We do need to be able to ventilate appropriately. We do need to be able to remove large amounts of air to reduce overheating. Fundamentally, though, my thoughts are that if we design the buildings better, we don't have overheating buildings and we can reduce it in other ways. There's no reason a building should overheat if it's adequately insulated and appropriately designed and performs as expected. It shouldn't overheat. We should be able to do that stuff competently and confidently with modeling, and then actually get that done in real life. The hard reality is we're not building what we say we build to the way we say we build it as a construction industry, and that's why we've had to then introduce things like approved document O. A big problem for approved document O is that 4 air changes an hour makes a huge amount of noise. It's a lot of air, and a lot of people just aren't, have buried their heads in the sand when it comes to approved document O, and suddenly they're required to get an assessment and it doesn't work. My I'm droning on a little bit. My other fault with approved document O is it clashes a lot with acoustics and noise control. So you then, you have openable windows, which means you have large amounts of potential background noise coming in. The idea is that approved document O is that you shouldn't have to compromise between background noise and outdoor air. But I think it could be improved. I think it will be improved actually quite quickly.
Thank you, Barry, and thank you for answering the questions in your presentation. I'd also like to thank everyone who's joined us this morning, and just remind you that this session has been recorded and will be uploaded to our YouTube channel soon, which can be shared with your colleagues. And with that, I'll wrap up, and thank you again for your time, and hopefully we'll see you next month.